LISE Picture Studio presents How to Make Rare Isotope Beams at Home. Sense of humor is a value we like to share here, and we hope you will have fun. There have been some who have already gone ahead and created their own experiments at home. Please do not follow their way. However, in our case, rare beams at home will not create a danger to you, your housemates, your pets, your property, or even your neighbors. After a hard day's work, we head home to get some rest. And we turn on the TV to watch our favorite sports team. It doesn't look like we're doing too good. Our brackets are gone. Not in a good mood, we begin to quickly switch between channels, so we switch over to the Discovery Channel, and suddenly, we find a program about nucleosynthesis and stellar evolution in the cosmos.
Nuclear reactions in stars and stellar explosions generate energy and are responsible for the ongoing synthesis of the elements. They are, therefore, at the heart of many astrophysical phenomena, such as stars, novae, supernovae, and X-ray bursts.
Around 260 stable isotopes found in nature, greater than 1 gigayears. Less than 1,000 known isotopes in 1966. Currently about 3,000 no isotopes. New territory, terra incognita, to be explored with next-generation rare isotope facilities as FRIB. They will produce more than 1,000 new isotopes at useful rates, 4,500 available for study.
What is last particle neutron-rich calcium isotope? How do we produce rare isotopes? What isotopes can be first observed in FRIB? Let's consider 58 calcium isotope production as an example. Why is 58 calcium isotope? Magic Z equals 20. Subshell at N equals 34. 58 calcium is the officially last neutron-rich calcium isotope, and furthermore was observed at the first time several years ago at MSU.
Learn how to make rare isotope beams. Do you know how to use email? Then you can learn how to make a rare isotope. It is that simple. Learn how. To estimate 58 calcium isotope production, we will use our powerful tool to prepare an experiment with rare isotope beams, the program LISE++. The code has been developed to calculate the transmission and yields of fragments produced and collected in a spectrometer.
Here's an introduction to our LISE++ package, which is maintained by the LISE++ group at Michigan State University and is freely available through the LISE site. Besides the LISE code, the LISE++ package includes codes like PACE4, Gemini, Global, Charge, Motor, and Itacha4. Started in the mid-80s at Ganil by Daniel, then in the mid-90s supported by Oleg, LISE initially operated on MS-DOS and consisted only of 14 C++ files. Currently, the entire package is more than 3,000 files in total and contains more than 1 million lines in the source. In 1998, LISE started operating under MS Windows, and in 2001, the LISE development moved to Michigan State University. In 2003, LISE++ became the new generation of LISE code, which allows the creation of a spectrometer through the use of different blocks. Different reaction mechanisms as fusion residues, fusion fission, abrasion fission, and Coulomb fission have been implemented in the code. Over the years, there has been growth in the LISE site statistics. According to these graphs, people in laboratories used to work hard on Tuesdays and Wednesdays, but not on Fridays. The LISE++ code may be applied at low, medium, and high energy facilities with fragment and recoil separators with electrostatic and/or magnetic selections. A lot of separator configurations have been developed and implemented in the LISE package. LISE provides a way to construct a fragment separated from different blocks, such as magnetic and electric multiples, solenoids, velocity filters, RF deflector and bunchers, material and beam, drift, rotation elements, and others. LISE provides a user-friendly interface that helps to seamlessly construct a fragment separator from the different blocks. Besides analytical calculation of the transmission and yields of fragments, LISE also has additional, powerful tools such as Monte Carlo simulation, ion optics calculation and optimization, and a variety of internal calculators working with physical, kinematics, evaporation, and radiation residue. Some well-known codes such as PACE, Hitachi, Global, and Charge have been imported to C++ and implemented in the package. Are you ready? Let's get started with rare isotope beam production. We begin with the basic principles of the creation of rare isotope beams: production, separation, registration, and identification. Production. For example, we are interested in the production of the 58 calcium isotope. First of all, it is necessary to choose the laboratory and setup of where to perform your study. In the case of Michigan State University, the reaction mechanism is projectile fragmentation. Then it is necessary to specify target and beam. Projectile fragmentation represents the two-step reaction of abrasion and ablation. In the first stage, we have to abrade our projectile. Therefore, a beam should have more or equal protons and neutrons than the fragment of interest. As you can see from the top right plot, we can select germanium stable isotopes as 70 and 76. Question: with what isotope can you produce more 58 calcium fragments? What is more probable, to strip 10 protons and 6 neutrons, or only 10 protons? And to what factor? From combinatorics, we have a factor 600 for 76 germanium over 70 germanium. Therefore, a primary beam should be more neutron-rich in the case of neutron-rich fragment of interest. In the case of a proton-rich fragment, vice versa, a proton-rich projectile should be chosen. The primary beam list can be in the laboratory specified page. What beam from the NSCL list of available beams is more favorable to obtain a 58 calcium beam? The answer is that an 82 selenium and 76 germanium are even. We observed two events in the NSCL experiments with an 82 selenium beam and with a 76 germanium beam. So, let's select an 82 selenium beam for our purpose and enter the corresponding primary beam information to the LISE beam dialog. Next up is the choice of target. Based on product of probability of fragment creation, called cross-section, and number of nucleons in a target, light targets are more preferable in projectile fragmentation reactions. Let's assume initially target thickness is 30% of range of a projectile in a target. Range is a target thickness that needs to stop a projectile. Special utility optimum target can be used to calculate a thickness for maximum production fragment rate. Our next basic principle, isotope selection. Let's estimate with the LISE code the yield after the target using a special icon, calculate transmission for all nuclei. Just after the target, the total rate will be 200 billion particles per second, whereas 58 calcium rate has only 1 to 2 events per day. How do we select 58 calcium? For this purpose, we are going to use a fragment separator A1900. A fragment separator is an ion optical device used to focus and separate products from the collision of ion beams within targets. First selection is by magnetic rigidity. We calculate dipole magnetic fields to correspond to momentum of the fragment of interest and select fragment by slits, named in the figure as momentum slits. You can observe the results of magnetic rigidity selection. We have enhanced the ratio of fragment yield to all products by 6 orders of magnitude. But it is still not enough, because maximum data acquisition rate should not exceed 1,000 counts per second. What is the next step? The next step is based on energy loss difference with the use of a wedge-shaped degrader. On the bottom right plot, you can see the distribution of residue fragments at the end of an A1900 fragment separator. Using focal plane slits, we can significantly decrease the total rate in detectors. Please see the final fragment residue plot on the right figure. With all of our selection steps, here is a summary of the results after the magnetic rigidity and wedge selections. We can provide purification of about 4 trillions with an A1900 fragment separator in the case of 58 calcium. Our final basic principles are registration and identification. The basis of PID, or particle identification. What do we want to know about particles? What does it mean we identified a particle? It means we know mass, elemental and ionic charges, and its energy. What can we measure? Total kinetic energy, magnetic rigidity, energy loss in a detector, and velocity based on the time of flight. If we need to know characteristics, then we have to measure at least 4 values. In our case, at a low Z in energy at 140 MeV per nucleon, we can assume Z, the elemental charge, is equal to Q, the ionic charge, and we need to measure only 3 values. We obtained the magnetic rigidity of a fragment with position measurement in the dispersive focal plane named image 2. Time of flight is measured between detectors located at image 2 and image 4, and the energy at position correspondingly by detectors at image 4. Here we can see correlation plots versus magnetic rigidity. The top plot shows particle identification plots in the case of full momentum acceptance. How can it be seen? It is hard to distinguish separation between masses. The situation was changed with smaller momentum acceptance of 0.6%, but we got a significantly smaller yield of fragment of interest. Is there a way to distinguish isotope separation at a high momentum acceptance? Let's obtain the values for atomic number, mass, and charge state from the measured values of energy loss, time of flight, total kinetic energy, and magnetic rigidity using equations shown in this page. Elemental and ionic charges and mass numbers should not depend on momentum acceptance. They are characteristics of an ion. Therefore, applying PID mathematics, we are able to separate nuclei independently from momentum acceptance. Shown in this slide are particle identification plots obtained in the NSCL experiment with a 76 germanium beam. The limit of previously observed nuclei is indicated by the solid red line. 15 isotopes were first observed in this work. Here we are planning to discuss 3 different methods of particle identification assignments. Here we can see the purpose of calibration with the primary beam. Shown here, we have unbound nuclei in the table of nuclides. For example, 8 beryllium, 9 bohr, 25 oxygen. Empty space in the known pattern can be proof of PID. Here we have fragment tagging with microsecond isomeric gamma rays. Gamma detectors surround a telescope where particles are stopped. The coincidence of registered heavy ions with gamma rays in a microsecond timing window allows for particle identification verification. Here, gamma spectrum is measured in the experiment with a 208 lead beam at MSU. Known isomer decay gamma lines are labeled. Almost finished. The first steps manuals and the detailed course of lectures, production of fast rare ion beams, can be found on the LISE++ site. Any questions? A thank you to all those who have contributed to the staff information talk.